Good morning. Today we're going to talk about pre-filtering. Alright, so what is pre-filtering? It's just applying any form of filtering, low-pass filtering, high-pass filtering, notch filtering to the input or output before we perform any estimation. So why might we be interested in doing that? Well, the obvious reason would be that we want to suppress some measurement noise. So for instance, imagine that you have recorded some data and there is a 50 hertz disturbance due to the electrical grid or something like that. We would like to get rid of that so that doesn't influence our estimation. Maybe we also want to suppress some kind of low disturbances, so disturbances that actually affect the dynamics. Or maybe we are interested in a model that fits in a certain frequency range, but we don't care elsewhere, and then we can kind of filter out the frequency ranges we don't care. Alright, so how do we perform pre-filtering? We start by noting that if we filter both input and output, so here I show the Laplace transform of the input u and the output y. If we apply a filter to both u and y, it's the same linear filter, then we don't actually change the input-output relation at all. So here we say that the output is our system we're identifying, linear system, times the input. And if we multiply both sides of this equation with a linear filter, it doesn't change the equation because for linear systems we can change the order, right? So if we apply h from the left, it's the same as applying h before the input here. So we can filter the input separately and filter the output, and we haven't changed the input-output relationship. So if we estimate the model using the pre-filter data, we will obtain the same model. All right. But if we now consider also noise affecting this system, and now I dropped the S here to make it a bit shorter. Now we have an additional noise term here. Then we actually do affect the input-output relationships somehow, right? Because now we are filtering away the noise. So this noise term might have a certain spectrum. So if that spectrum is completely flat, then we don't gain much by filtering. But if this spectrum, for instance, has a peak, for instance, this 50 hertz disturbance peak, then we can choose H to remove that peak, all right? So I say here that if we know the spectrum of n, the optimal choice is to select our pre-filter H as the inverse of n. And if you are interested in proof of this optimality here, I suggest reading the book by Lennart Jung, System Identification Theory for the User. Alright, so we can pre-filter our input-output data by applying the same filter on both the input and the output. Okay, so how should we not pre-filter our data? So if we don't filter both y and u, then we're not estimating g anymore. We're actually estimating something else, right? So if we apply filter to only y, which might be perhaps the most intuitive way of doing it. We have some measurement noise in y. Why don't we just filter y? Then we're actually estimating the combined system g times the filter rather than only g. All right, and that's typically not what we want to do. We will see an example how that doing that actually biased the estimate. If we have a nonlinear system, G, so here I still write it kind of our system equation on operator form, then G and H is not the same as H and G. They don't commute. So filtering before or after the dynamics obviously plays a big role for a nonlinear system. And then we can't simply apply a low-pass filter or any filter on the input and output and expect to still estimate the same system G. However, there is another way we can do it in this case. So if we are using a prediction error method for a nonlinear system, we can compute the prediction errors and then we filter those instead. All right, and that's for linear systems that's equivalent, but it has the drawback that we need to repeatedly apply this filtering during the optimization. But if we do pre-filtering instead, we just apply the filtering once. That's computationally cheaper. But this approach of filtering the prediction errors work also for nonlinear systems. All right, so I finish here by saying, is it ever okay to filter only the output? And yes, that might be okay if you have frequency ranges where the gain of your system is extremely small, so typically for high frequencies. Then the output is consisting of only noise for those frequencies. So then applying a filter H doesn't actually change anything because G is already 0 for those frequencies. So if you remove even more of that frequency, you still have 0, right? So you're just affecting the noise spectrum then. So then it's okay. But that requires, of course, that you already have a rough estimate of the frequency response of the system you want to estimate. All right, so now we're going to see a little example of this. I load the control system identification package and plotting and so on. This just set the plotting theme to dark to match the background here. The system we're going to identify is a simple second order transfer function. It looks like this in the Bode plot. All right, and then I discretize that to simulate it, and I draw some random noise as input. So then I simulate this, and then I add a periodic disturbance with a particular frequency, 0.3 radians per second. So I just add that disturbance to my output. And we show the true output here in red, and we see the noisy output in yellow. So we see the noise is fairly large. We have more than doubled the amplitude in the output. But say that we happen to know this frequency. This frequency doesn't correspond to the electrical grid, but say that we know this frequency for some reason. Then we can, first I package this data into an identification data input. So here I use the noisy version, but there is no noise on the input. So if I just perform estimation with this data set, I estimate a model of order 2 with a prediction error method, because model of order 2 because we had a second order transfer function. Now we plot the true system here in red and the estimated model in yellow. And we see that the estimated model is quite poor. I show this green line here is the frequency of the disturbance. So we see that the model here, the identification was severely impacted by this periodic disturbance. And that's to be expected, right? Because the disturbance is enormous compared to the true output. All right, so we have to do something to get a better model here. So the first thing we do is we pre-filter with a known noise model. All right, so if we load the DSP package, we can construct a digital filter. So there is a constructor called just digital filter, and I say I want a band stop filter. So that's if you make the stop band very small, it corresponds to a notch filter. So here I say I want to stop frequencies from 90% of this known frequency to 110%, so plus minus 10% of the frequency I know our disturbance is at. And here this frequency is in radian per second, and I divide by 2 pi to get it in hertz, which is what the DSP package wants. And I say the sample frequency is equal to the sample frequency of the dataset. And the design method is a Butterworth filter with 2 poles. All right, so that gives me something called a zero pole gain filter from the DSP package. I can convert that to a transfer function from the control systems package by calling TF. And I do that so that we can plot the Bode plot of the filter. So we have it here. We see it has a notch at the particular frequency we chose here, the frequency of the disturbance. All right, so to pre-filter with such a filter, we can just say pre-filter D, and then we just pass in this band stop constructor here. Pre-filter actually has yet another constructor where you just pass, let's see here, where you just pass lower and upper. So you can immediately pass in the band stop limits to this prefilter function, and you don't have to bother with creating this band stop object here. So now we look at the input-output data again. We see that now we have the unfiltered noisy output in red, and we have filtered that to obtain the orange line here. And we see that we applied the same filter to the input, but the input doesn't contain that much energy on the filtered frequency, so there is almost no change. But there is a small, just barely perceptible change in the input as well. All right, so now we will try to estimate the model using this pre-filtered data set. So here I call new prediction error method with the filtered data set. Once again of order 2. And now we plot the pre-filtered model result here in green, and we see that it's much closer to the true system in red. It's not perfect, but it's very close, much closer than the naive estimate here without any filtering in orange. So this indicates a successful pre-filtering. Right, so this is one method of handling noise using pre-filtering. Another method is to actually estimate the noise model. So say that we don't know a model of the noise. We can actually allow a prediction error method to estimate that also. So by default, the prediction error method does perform a noise model estimation. We just need to make sure that we give the prediction error method a sufficiently high model order to actually identify a noise model. So in this case, we have 2 poles from the system we're trying to identify, but we also have a periodic disturbance, and a periodic disturbance requires 2 poles to model. So if we estimate the model of order 4, we should ideally have a nice result. And here I have provided a custom initialization to the prediction error method. I say I want to increase the prediction horizon from the default slightly to have a nice estimate here. It says success, and it has converged. And if we plot that estimated model in the Bode plot, we now see that actually the green curve is exactly on top of the red curve here. So it has identified the true system with an extremely high accuracy. This is obviously unrealistic. This only works because we have simulated all the data here. But nevertheless, it shows that we were able to actually recover the true system even without any pre-filtering here. And we can ask the estimated prediction model what the noise model is. So we can plot that as well. We can say here Bode plot of the noise model of this predictor model. And we see that this noise model has a sharp peak at exactly the frequency where we added the disturbance. So this is a good indication that the prediction error method actually found a model of the noise, and we're able to remove that. All right. Yeah, we can have a look at the noise model here, and it's of a 4th order in this case. We can also try another identification method that can identify noise models. So here we call a function called arcs-AR. So this is an autoregressive model with external input, and it has an autoregressive noise model. All right. And it takes the model order, the number of coefficients in the numerator polynomial, and the number of coefficients in the noise model. So ideally this should be 2, 2, 2, because that's what our true system actually is. But this is also an iterative estimation method, and if I use 2 poles, we see that it doesn't actually converge very well. Here we have the true system in orange and the estimated model in, the true system in red and the estimated model in orange, and it doesn't look very good, so it hasn't really converged. But if I increase the model order, we now see that the orange curve is on top of the red curve, and we can't see it anymore. And the noise model is exactly peaking at the noise frequency. However, we can call, so here we have the true system model, and here we have the estimated model after reducing the model order using mean real. So we see that it has actually now recovered the true model, but it recovered the true model after a model order reduction. So we see that the estimated model is of order 4, And if I call min real, it's now order 2, but now the order 2 model matches the true system PD here. All right. So the last thing we're gonna look at is what happens if we filter only the output. So this, I said in the beginning that we should ideally not do this because that would bias the estimate. So here I create a new identification data object where I use the filtered version of the output, but the unfiltered version of the input. And then I estimate the model of order 2. And now we see that I still have some bias in the model. So I have actually not recovered the true system model here. So filtering only the output is not a good idea, at least for linear systems. All right, and this concludes the video. Thank you.